All right, good morning. Okay, that's sad. Good morning. Good. So we got the exam coming up a week from tomorrow, which, if you remember, is also the election day. And I told you the first day of classes, do what you need to do to vote, if you can vote on that day. So plan ahead if you haven't done so already. Exam 2 will be at the same place as last time, same time. And the seating block, just based on glancing these, look about the same. So again, find out where you need to go. Your TA will be assigning seats like last time. You should get them in recitation tomorrow. So that's the exam. And I'll talk more about the exam in the coming days. There is an exam study guide posted on the course webpage. That's from a couple years back. I can't take credit for that, but it's there. It's got a list of all the things that we have covered. And once again, I'll talk more about the exam in the coming days. Also, if you want to plan ahead, the final exam schedule is posted. You just Google Purdue final exam schedule fall 2016. The top link should take you directly to a place where you can look up all your final exam schedule. Okay, today we're going to look at section 2, chapter 16. We'll look at these things called line integrals. What a line integral is a generalization of an integral with respect to x or an integral with respect to y. So how does this work? In a two-dimensional situation, when we only have x and y to worry about, and we have some kind of function, let's call this y is equal to f of x. Okay, we know we can integrate from a to b to get the area and all that stuff, right? So if you look at this situation here, what we're really doing, remember, is to accumulate the value of f of x as we march along some kind of line segment on the x-axis. Accumulation of f of x on the x-axis from x is equal to a to x is equal to b. And we could do the same thing with y. We can march along the y-axis from some a to some b of the value of the function f of y. Okay? So in 2D, those are the only choices we have. We either march along the x-axis or the y-axis. We have no other choice. Now in 3D, we've got to remember that we have some kind of height over this picture now. Okay, so imagine you have z is equal to f of x, y, something that's above this plane right here. And let's suppose that the projection of that, some kind of curve, looks like this. So this is the called that projection of some kind of curve, r of t, onto the xy plane. So the important thing here is, notice now we can integrate this function along the x-axis, along the y-axis, or along some arbitrary curve in that plane. along any curve on the xy plane. Not just the x or the y-axis. We have more choices now. And what we're doing is the same thing. We're accumulating the height of this curve, some kind of height z, and now we're going to have to march along this curve right here and accumulate that value in exactly the same way we did integral with respect to x or y. So this is a generalization of what we have been doing, the integration that you know. But the idea behind that is exactly the same. Now we can just march in any kind of curve we want, not just x or y. All right, so the new notation that we have to get used to seeing is this. You write an integral sign with a c at the foot of it, and this c here is the integral, the curve that we integrate along. Again, in the 2D world, that's simply x or the y-axis, but now it can be just about any curve. And this ds, this is the elemental, well, let's call that the length element along the curve C. Okay, so instead of dx, now we integrate ds, where s is some tiny little segment along the curve C. So suppose this is C, then a little ds would be this thing right here, some tiny little segment along that curve. Now, one way to do this integral here to calculate the integral along the curve C of f of x, y ds is to parameterize the curve C. So we're going to say that C is some space curve R of t, which is a vector function. The x component is some x as a function of t, and the y component is some y function of t. And we allow t to go from some a to some b. All right, so we parameterize this curve C as a space curve with t being the parameter. Remember the arc length of this thing, of this curve, we saw this formula earlier, called that S, is the integral from a to b dx dt squared plus dy dt squared, all under a root with respect to dt. And what that thing we integrated really was just ds. So that means to get the arc length, we integrate a bunch of tiny little elemental arc length, accumulated that from a to b. So this stuff right here, this is our ds. which is the ds we're going to be using in the arc, the line integral. All right, so therefore, the line integral we're trying to do, f of xy ds, can be rewritten as an integral from a to b. The function f, now instead of with x and y being the variables, we have to change to t. And then ds, we'll borrow this expression here. dy dt squared, that's an x dt. Okay, so that's how you can compute the line integral if you parameterize that curve as with the parameter t going from a to b, whatever a and b you want them to be, as the situation demands. So if you think about this, the name line integral really is not a very good name, because we're not just integrating along a line, we're integrating along any kind of curve. So really a curve integral is a better name, but historically it's always been called a line integral, and we'll just keep calling it that. But just remember the word line in that context means any kind of curve. Okay, let's try that out on something. Let's find the line integral along C of y cosine of x ds. Where C is the line segment from the point 0, 1 to the point 4, 4. Okay, integrating some function of xy along some kind of arbitrarily defined curve, a line in this case. Let's try to visualize what's going on. 0, 1 is right here. And then 4, 4, let's say, is right here. And what we're trying to do here is to integrate y cosine x along this segment. Okay, so let's follow what we did on the previous page. First thing we want to do is to parameterize this curve C with a parameter t. Remember how to write a vector equation for a line segment between 2 points? We did this way back at the beginning of the semester. Remember? How about just the general form of an equation for a line in a vector form? No one? How about this? Some vector to a point plus the parameter t times the vector v, giving us the direction. Remember? This was a while back, but, right? A vector to a point, and parameter, and direction. So in our case here, we need a vector to either of these 2 points. So just pick the first point. Vector to the first point is 0, 1. This is a vector from the origin to that point, plus the parameter t. And how do we find v? How do we find this vector giving us the direction? What would it be for this case? Right, yeah. Think about how much x you need to make up to go from 0 to 4. You need to go make up 4, right? So that's the direction you need to go. How much y you need to make up to go from 1 to 3? You need 3 more to get to 4. So that would be the direction. So let's say, think of it this way. If you're standing at 0, 1, how do you get to 0, 4? How much ground do you have to cover to get to 4 for x? You got to move 4 units to the right. Therefore, this number here. If you got 1 already, you want to go to 4, you need to make up 3 as your deficit. So that would be your v vector here. Let's rewrite this in a more compact form. This is simply 4t, comma, 1 plus 3t. What is the interval of t for this if we parameterize this way? What does t have to be to get to this point? 0, right. What does t have to be to get to here? 1, yeah. If you formulate it this way, t is always going to be between 0 and 1. If you take the initial point plus t times the difference between the two as your vector, then it's always going to be 0 to 1. Okay, remember, this is our x of t. This is our y of t. Looking back a little bit, we're integrating y cosine x. So we're really integrating y cosine x along ds. Now we got to calculate ds. ds is just a tiny little fragment of the arc length of this. dx dt squared plus dy dt squared under the root, and then the differential time t. dx dt is 4. 4 squared is 16. dy dt is 3. 3 squared is 9. 16 plus 9 is 25. Radical that gives us a 5. And we, of course, only take a positive root because this is a differential length, a differential distance. That thing has to be positive. Okay, so far so good? All right, now we can rewrite our integral. So the line integral we started with now becomes an integral from 0 to 1. Y becomes 1 plus 3t cosine of x ds 5 dt. Okay? That 5 is irrelevant as far as the integration is concerned. We'll move it out. And then we'll worry about the integration here. Okay, how do we integrate this? Parts, very good. right? So what should u be? You're on a roll. What's that? 1 plus 3t? Good. And dv is the other choice, whatever we didn't choose. Okay, remember the order to choose your u? Yes, no? We had a little, remember the order? Logarithmic, inverse trig, algebraic, trig, exponential, right? Remember that? That's the way you choose your u and dv. So here, this is an algebraic a, and then this is a trig. So we pick this before the trig. But anyway, you should know how to integrate by parts. All right, du is 3 dt. V is the integral of that, and that's going to be 1 over 4 sine of 4t. Okay, and then this will turn into uv minus integral v du. U v 0, 1 minus integral 0, 1 v du. I have a 1/4 and a 3. I'm going to move it out just to get things out of the way. Okay, so what's left here is not difficult now. So this is 5 times t is equal to 1. We get a 4 times 1/4, that's a 1. Sine of 4. When I put in a 0, I get nothing because sine of 0 is 0. I can integrate that. I get positive 3 over 4, 3 over 16, sorry. Cosine of 4t. Again, t is from 0 to 1. Okay, keep going. 5 sine of 4 plus 3 over 16 cosine of 4 minus 3 over 16 cosine of 0, which is a 1. All right, and that's it. That's the value of the line integral we get. Questions? Okay, good. But it turns out that parameterizing with respect to t is not the only, yeah. Oh, that's my, when I parameterize the curve C, this line right here, this r of t here, and we found out earlier that to make this giving me the original point, t has to be 0. To get to the final point, t has to be 1. So I know to get all of these dots between the 2 points, I just let t go from 0 to 1. Yep. Other questions? Okay, so like I was saying that we don't always have to parameterize with respect to t. We could use x and y. For example, let's look at a very simple curve here. If we're talking about the curve that's described by y is equal to x plus 1, I want to go from 0 to 1 to 5. So we're on a parabola going from here to here, going in that direction. And here are some of the choices we could use. The first one is to deal with t, right? The first one is to say x is equal to t and y is t squared plus 1. And let's see, to get to the point 0, 1, I can let t be 0. To get to the point 2, 5, I just let t be 1. Rather 2, right? 2. So that's the same parameterization we use, the same type of parameterization we used in the last example. That's with respect to t. Or what we could do is to describe this using x as the parameter. So x is x, of course, and y is equal to x squared plus 1. Then we can say x goes from 0 to 2. And it's really the same parameterization as t. The only thing different here is what you call your parameter. We could also use y to parameterize this. If you use y to parameterize this curve, then y is y, of course. X is the square root of y minus 1. And now we let y go from 1 to 5, right? So what this means is that when you do a line integral, f of x, y ds, this ds here, it really could be in terms of x, y, or t, depending on how you parameterize the curve, which you have lots of different choices to do that. These are not the only 3 choices to do that. You can parameterize essentially in any way you want, as long as you can somehow reproduce that curve. Here's an example of an integration of using x and y as the parameter. Here we're integrating x plus y dx plus x squared dy. So note essentially we're forced to use the x and y as our parameter in some way. We have some flexibility here, but we have kind of led down this path already by the integral presented to us. And let's make C a little bit more complicated than last time. Let's let C be a line segment from 0, 0 to 1, 1. Then a line segment from 1, 1 to 2, 0. So we follow the first half of the trip is 0, 0 to 1, 1. Then we change our path, go from the 1, 1 to 2, 0. All right, so what does this look like? We go this way first, then we go that way. Okay, we cannot come up with one equation to describe this kind of path. So what we got to do here is to break it into two line integrals. Let's call the first half C1, call the second half C2. So we're going to do an integral along C1 first, then do an integral along C2 and add them together. All right, so let's parameterize C1 first. We're going to try to stick with x and y as our parameters. Okay? So along C1, the equation is simply y is equal to x. Right? It's a straight line going from 0, 0 to 1, 1. The slope is 1. The intercept is 0. So it's simply y is equal to x. And to go from here to here, we let x go from 0 to 1, which you can see from the picture. X starts here and ends here. And dx, of course, is equal to dx. And if you take the derivative of this equation, then dy is also dx. Okay, so I can take care of the dx, just dx. I can take care of the y because y is equal to x. And then dy is equal to dx. Because the derivative of y equal to x is 1, so dy is dx. Let's look at C2. C2 is going from 1, 1 to 2, 0. Writing the equation of that line is pretty easy. Y turns out to be 2 minus x. And x is going from 1 to 2. Now this time dy is negative dx. Okay, so I need these pieces of stuff to go into my line integral. I've made a choice here to stick with x as the parameter. So y has to go and dy has to change to something to do with dx. Let's write out the integral here now. We need two pieces, one for C1, one for C2. On the first half of the path, x goes from 0 to 1. X plus y becomes x plus x. Right? This is x because y is equal to x on C1. Dx plus x squared dy is dx. On C1. Okay? Now we need to do C2. For the second half of the path, x goes from 1 to 2. x plus y becomes x plus 2 minus x. And that's because y is equal to 2 at minus x on C2. So x plus y is x plus y. dx plus x squared. And then dy on the second half is negative dx. Okay, so once again, this is the C1 integral. And this here is C2 integral. So far, so good? Any questions so far? Basically, once you got to this point, what follows is relatively easy. Okay, let's finish that up and see what we get. The first half of this really can be written as 2x plus x squared dx. The second integral is integral 1 to 2 of 2 minus x squared dx. Right? X is canceled out in the first half of the second part, and then we have a 2 minus x squared dx. Then the integral is x squared plus x cubed over 3, 0, 1, that's C1, plus 2x minus x cubed over 3, 1 to 2. And let's see, what do we get? We get 1 plus 1 over 3, that's 4 over 3, plus, that's a 4 minus 8 over 3, minus, that's a 2 minus 1 over 3, and let's see, this is 5 over 3 minus 8 over 3, that's minus 1. And we have a 4 minus 2 minus 1, that's a 1. Turns out to be a 1. Okay? Okay, so basically anytime you got a path that's not smooth in some point, that's when you got to break things up. Here we got a little kink here. That's not a smooth transition. We have to break it up. Okay, so what does this number 1 mean? There are many, many interpretations of what we just did. Now, one interpretation could be, simply could be the area under that curve in the z direction projected down onto that space curve. But it could have other interpretations too. We'll look at one of the applications of this, and next time we'll look at a couple more. One of the applications is you can find the mass of a certain curved material. So for example, if rho of x, we can go three-dimensional. If rho of x, y, z is the density, so it's constantly varying, then the mass of a thin wire in the shape of a space curve is m is equal to space integral along. You integrate the density right? So this will give you the mass. All you're doing here is you're approximating the mass of a short segment by taking the density of that of a point times a little short segment nearby that, and you accumulate that all the way from the beginning of that wire to the end of the wire. So that gives you the mass. You could also find the center of the mass. We're dealing with 3 dimensions now, so center of mass can be found by using this formula. And this should look very familiar to you because we did something with the lamina a while back. These things are derived in exactly the same way, right? X bar is 1 over m, line integral x rho ds. Y bar is 1 over m, line integral y rho ds. And finally, z bar is 1 over m, line integral z rho xyz ds. And again, these formulas come from the same principle that we use to derive the formulas for the mass and the center of mass of a thin plate. Exactly the same idea. In 2D, we have almost the same thing. You could just have a wire that lies in the x and y plane. So rho is, again, just the density along the arc length. In 2D, there's no z, so just the x and y bar. All right, so that's one application of using a line integral. Really, a path integral is a much better term for that. So if you could describe the shape of this wire as a space curve, then these things will tell you the mass and the center of mass. So imagine you have a length of wire in whatever shape. How would you balance that piece of that wire on your fingertip? That's where the center of mass tells you. All right, let's try this on something. Let's try this one. We have a thin wire in the shape of the first quadrant part of x squared plus y squared is equal to 1. And let's imagine our density is rho of xy equal to x times y. That we know is a circle, right? Radius 1. So we got a wire bent in this shape. A quarter of a circle. First of all, you got to parameterize this. Remember how to parameterize a circle? What would you let x be? Right. What if the radius is 9? Right. So in general, it's the square root of the radius cosine. So that way, when you add it together, you get this equation. So, yep, you're on the right track. Cosine of t, and then sine of t. This will give us the circle we want here, radius 1. Just remember, these things added together should give you radius squared, right? Where does t go from, and where does t go to, if we parameterize it this way? Yeah, 0 to pi over 2. Good. So now we got the parameterization. ds, derivative of this thing squared, minus sine squared plus cosine squared under a root dt. And this turns out to be a 1 under the root. Radical 1 is 1. 1 times dt is dt. So ds turns out to be dt. So that's very convenient. Let's calculate the mass. We parameterize to use t. So we go from 0 to pi over 2. The density is x times y. And on this curve that we use to parameterize that, x is cosine, y is sine. So rho becomes cosine and sine times sine. Right, so this is our rho, density. ds, we calculated to be dt. So that's pretty nice. That's ds. Okay? So how do you integrate this? How do we integrate cosine times sine? Substitution, yeah. With u be equal to, doesn't matter, right? Doesn't matter what u is equal to in this case. Let's let u be sine. Why not? du is cosine of t dt. All right, so this integral turns into, we've got to be careful with our integration bounds now. When t is 0, u is sine of 0, still 0. When t is pi over 2, u is sine of pi over 2, and that's a 1. And then this will be u times du. So that's u over 2, u squared over 2, 0 to 1, that's 1/2. That's our mass. For x bar and y bar, same idea. The integration is a little bit more complicated, but for this one, it's not very difficult. I'll skip the y bar and x bar. You know how to do it. All right, so that's the first part of the line integral that we're going to cover tomorrow. Well, not tomorrow. On Wednesday, we'll look at more applications of this thing. Okay? All right, see you on Wednesday.